Welcome to Biological Reactions to Materials. What I would like to do today is talk about surface energy, which you will be familiar with. The surface energy is the amount of excess energy that it takes to make new surface. But what does that mean chemically? Well, we know that from normal material science subjects, so we can imagine a surface, and if it was something like glass, so it would have SiO(Si) groups on it, and we've broken them, then we've got some bonds left over, and they will typically form OH when they're exposed to the atmosphere, and that is the excess energy that's left over, what it requires to make this, rather than the surface, because it's a little bit more energetic, this bond, although it's capped. If we think of this in terms of solutions, if we're taking a liquid, if we take water, it's a polar liquid that can do hydrogen bonding, so it's got a higher energy. If it forms a solid, ice has a high surface energy, approximately equal to that of water. If we take something that's non-polar, so we take a standard polymer, polyethylene, say, we have a CH3 group on the outside. We don't break the polymer to get to that. Typically we don't break molecules when we're cutting our polymer. We end up with some CH3 groups on the outside, maybe some of the odd more reactive group. Let me try and focus a bit better. And if we do that, the surface energy of this will be lower. So we would imagine, if we're going to bring something up to it, that it is easier to stick things onto this than it is to stick them onto this. And we saw that in a different course, you and I, where we want to paint a surface, we want to attach something to it, we need a high surface energy, and so something like silicon dioxide, glass, is easier to paint than polypropylene. It's almost impossible to paint polypropylene. The paint falls off, it's hard to print on it, it's hard to write on it. It's easy to write on glass, you can use anything. Apart from pencil, it doesn't work very well because it's smooth. If we take some water and we put it onto these surfaces, the water will spread on the glass almost completely, goes down to a very, very flat kind of drop on the surface, and on polypropylene it sits up as a little bit more than half a ball. So the contact angle of the water on it is dependent on the interaction between the water and the surface, but we can think of it as the water directly, the water molecules interacting with the bonds. So here we've got a polar water interacting with a polar surface group, and here we've got non-polar. If we make it more complicated, so we make these groups acidic or basic, then they will also have effects, or we make them actually reactive in some way. But for the purposes of this topic, we're not looking at reactions, chemical reactions going on. We're more interested in what is going to be the interaction. Is it going to stick? So now we want to take these in the air, and we apply something. It will typically stick to the thing with the high surface energy, preferentially, if it can, because globally the energy is lower if we take our high surface energy things and stick them together. So we take our water and put it on here. If we allow it to choose by letting it evaporate, it will end up on the silicon and not on the polypropylene, polyethylene, whatever it is. But there's a new factor that we have with our subject, that typically we're not in the air. So in the air, obviously things will stick to the thing with high surface energy. But in the water we have a three-body problem effectively. We have the surface, we have the water, we make the water blue, and if my blue pen works, and we have the other surface, something else. So if we take these, for example, the silicon dioxide, the glass, and the polyethylene, are not particularly interested in each other. If we put water in between, they're still not that interested in each other, because the water is somewhere in between the two. The water is going to stick to the glass, it's not going to stick to the polyethylene, and nothing interesting will happen. But if we put a second piece of glass in, the second piece of glass is, if we've activated it enough, slightly more reactive than the water, and so it will tend to stick to the other piece of glass. We'll tend to end up with two pieces of glass close together. Usually there's some water trapped in between. But if we go to this one, a more interesting thing happens. If we take our polyethylene and another piece of polyethylene, they are better, there's less surface area of water, if we put the two polyethylene surfaces together. Now that all seems obvious but not very interesting, so let's get on to our actual subject. So here in our real subject, just checking my microphone's working, here in our real subject we have a protein or a biomolecule of some kind, and we have the surface. And the surface could be glass, and it could be polyethylene, it could be anything. And what we want to know is, how can we predict whether this protein is going to stick to the surface, and it is in water. What we discover is the closer that our protein is to water in its surface properties, so the energy of the material and the polarity and the hydrogen bonding ability and the charge, the closer it is to water, the more likely it's going to be in the water. If we go to the surface, we can bond to the surface if it's got high energy, and we can also end up stuck to the surface if it's got very low energy. So if our surface is polyethylene and our particle is hydrophobic, it will be pushed out to the side. And you have probably seen this. If you try to wash up and you've got greasy pots, then the grease tends to stick together. Or a pan, our nice non-stick pan, if we've got it in greasy washing up water, the greasy balls, so the little islands of fat, will then go and stick to our pan when we take it out. This is made slightly more complicated by what's going on with our protein. So you all know what a protein is. It's a chain of amino acids that probably has some kind of extra modification on the outside, but for the purposes of this we're going to draw it as blue and red regions. So if we have a protein that's got hydrophobic bits, let's make it a bit longer because it makes it more sensible. So we have a chain of protein, and it will have hydrophobic and hydrophilic sections. So let's make a few hydrophobic sections on there. So let's have the end hydrophilic is blue, hydrophobic is red, because otherwise it doesn't agree with what I've drawn there. If we take this protein and we fold it, the blue parts, which are going to interact with water, then the hydrophilic parts, will remain on the outside, and the red parts, the hydrophobic parts, will fold into the center preferentially. It isn't 100% so, because obviously proteins have other functions, but one that is floating around in body fluid, that's its job, floating around in body fluid. So maybe albumin, a protein that's in egg white and that's in blood, it's in body fluids mainly, so sperm and other things, are viscosity modified by albumin, a protein whose main function is to modify the osmotic potential and viscosity of liquid. So let's fold this protein up. Here it is. It's just a diagram of a protein. It's not what they really look like, but this is the concept. They have an inner core that's hydrophobic mostly, and an outer region that's mostly hydrophilic, and that allows them to be suspended, to be dissolved in water. Suspension and dissolution is whether you have particles moving around or molecules, but in the case of proteins we're in a weird in-between zone where we've got gigantic molecules that are otherwise the same as really, really tiny particles. You can make a small particle of gold that's smaller than a protein molecule, and likewise we could have a bigger molecule, but proteins are very big molecules. If we take this protein and we move it up to a surface of glass, the hydrophilic groups, which are higher energy, will tend to bond to it, and they will tend to bond to it specifically so that it will usually be nitrogen groups on the outside that attach to the glass. If we bring it up to a hydrophobic group, it is possible, and very likely, that the inside of it can turn inside out. So this side can go through, so let's draw it on there, and the hydrophilic part goes into the water, this little hat, or it spreads out completely flat. Once we've done that, we might have damaged it permanently, and we see this if we take a solution of protein, so we take some egg white for example, and we either work it, so we beat it and that stretches the protein out, then it can't fold back up again on its own very easily. It can do it, but not very easily. Or we just leave it in the air. The layer on the top is different to normal water. It doesn't behave like water, and it doesn't behave like soapy water either, because when the protein is in the surface, imagine the surface is the same as a hydrophobic layer, it has very low surface energy out here because it's air. Nothing is there to bond to the water. Water doesn't like to do that, and so exactly the same thing happens. This protein can stick on and let go, but there's a question as to how damaged it is when it goes back into the solution. It depends. Very often it can. Albumin can usually refold, other proteins often can't. What that means is that we have a surface, or we have a stickiness from our protein to both hydrophobic low energy surfaces and hydrophilic high energy surfaces, but if they are somewhere in between, like water, then it's not so sticky, and that means we end up with the following type of behavior. So this is the type of curve that we get with low energy. The kind of Teflon repellent surfaces actually cause our protein to stick more with a hydrophobic sticking because water is in there. The water causes it to stick. In fact, in the air it would not stick at all. The interaction is very low, but the water effectively evicts the dissolved protein and pushes it to the surface. We end up with two hydrophobic things sticking together because the water is rejecting them both, and it's lower in energy to have them two together. We have a sort of optimal region of least sticking, if that's what we want to do, and then we can stick more as we increase the surface energy in the other direction. Sometimes people draw it coming back down again for various reasons up here, but this is the kind of curve that we expect because of the water being there. That's important because obviously we're going to be interacting with liquid that contains water mostly, because we're in the biological system. Obviously there is another issue, which is specific attraction. So if we have our hydrophobic surface, it will attract, or it will attach lots of protein, lots of hydrophobic things, but something like an organism will still struggle to attach because it cannot make a chemical bond. Down here, even here, where we can make chemical bonds, if we have something specific that we know we can attach to, so depending on what it is, if it's a byssus, the hairs on the fibers on a muscle, the freshwater mussel for example, it reacts with metals. It's cross-linked using metals, and it attaches very strongly, forming a chemical bond. And it can do that pretty much anywhere, but it can either do it with a hydrophobic bond, which is not a real bond, it's just an interaction, or it can do it with a real bond on this side, which is probably stronger. If we have something like snail slime, it will stick all over, but it will be better where it's sticky, and it will have trouble getting its stuff back off. And down here where it's hydrophobic, the snail will stick in a different way because its slime is slightly soapy effectively, and it can bond to it even underwater. But down in this region there will be a problem. If it's raining, the snail won't be able to stick. If we think about charge is obviously another force that can be involved. It does affect the surface energy, of course, but it is more specific. If we take a negatively charged surface, we can imagine it will have a different effect, respond differently to a positively charged surface. These are the ones that you will probably know from biochemistry. So this is a carboxylic acid group. It's negatively charged in neutral conditions when it's deprotonated, depending on what the rest of the group is. pKa can be somewhere between 2.5 up to 5, maybe even slightly higher, depending on what's on there. This is an amine, and depending also on what's on here, it behaves as a base. It's accepted a proton. If it loses a proton, it becomes zero charge. Likewise, the acid can grab a proton and also become zero charged, and depending on the pH, some of them will be charged and some of them will not be. But inside normal physiology, we're at a relatively stable pH, apart from in a stomach or somewhere really evil. But in most parts of an animal and most parts of a plant, we're relatively close to pH 7, and then we can predict what charge our surface will have. It turns out that it matters. So if we take a glass surface, for example, glass is almost always negatively charged, and glass has an effect on blood clotting, which is in the next sort of video. That is specific. If we take a positively charged surface, it doesn't do the same thing. So if we take a biological system that is recognizing these acid groups or recognizing a negative charge, it may be fooled into doing something which we can think of as good or bad, depending on what our goal is. So we can plan for it, or we can plan against it. Just as a final thing, I know a real case where this is used. So the real case where this is used is when you go and have your blood tested. The problem with blood is that it has a lot of cells in it, and the red blood cells are not very useful for many things. So you obviously need them if you want to measure anemia, which is related to the amount of iron, or if you want to measure oxygen carrying capacity or something. But for most tests of blood, the red blood cells are in the way and they're coloured, so they cause problems. If we're going to have a test, let's try and get it to focus, if we're going to try and have a test that will have a colour change, then obviously we need to get rid of those red blood cells. Likewise, if we want to measure antibodies in the blood, so for corona, for example, for allergy tests. So alternatively, we might want to look at white blood cells. There are a lot less white blood cells in the blood than there are red blood cells, and obviously we would like to get rid of the red blood cells before we do that. And if we want to do if we want to measure just proteins in the blood, we would also like to get rid of the red blood cells for obvious reasons. Anything that you can get rid of without costing your effort, without making your test more difficult, without changing the volume, is good. So how are we going to do that? We cause the blood to clot. And the simplest way to do that is to throw in a polyethylene ball. Polyethylene ball is good because it's hydrophobic, and it causes blood clotting by making the blood think that it's not inside the body. Blood doesn't think, obviously, but it detects through mechanisms that you see in the other video. It detects that it's outside the body, and that causes it to clot. And when you take one of those little blood tubes, and it is for a antibody test or for a white blood cell test, there are little P's in the bottom of some polymer, and they're there for specifically that reason. The other thing that is possibly in the blood container, but not at the same time, is a chemical to stop the blood from clotting. Because obviously, if we want the red blood cells, we have to stop them from clotting, because eventually they will anyway. They're outside the body, and they will find something, even an air bubble, that will make them think they're outside the body. An air bubble in a blood bag is enough to do that, and then they'll start to clot, and eventually it will just turn into a horrible jelly. That's what we want for the blood sample, because we want to take the plasma, the little juice in there, and detect that. We want to get rid of all the iron and all the red colour and all the blood cells, because they don't have nuclei, so we don't have to worry about those. If we want to do any DNA testing or anything, we want to do that as well. But now we've got our alternative situation. We want to preserve the blood and prevent it from going hard. We need to do something else, and that would be to take away the calcium, because if you look in the other video, you can see that the chain of reactions that causes blood to clot relies on calcium. So if we take the calcium away, it can't clot. Obviously that means that the blood is somewhat damaged, so it can't do the thing it's supposed to do. But if you inject it into somebody, their blood will dilute the chelating agent, takes the calcium out, and allow it to refunction. Or you can add some. But if you add some, obviously it may cause clotting. Okay, that'll do for today. We'll stop there.